Good morning, everybody. Can you hear me? Hello, can somebody tell me if they hear me, please? You can hear me? All right, thank you. All right, it's 8 o'clock. We'll get started here. How many people we got so far? 7. All right. I remember last semester, I had classes sometimes when one person would turn up. Generally, I've had like 20 turn up to these 8 o'clock sessions. I know it's early, but yeah. I hope other people are watching these videos later. I think they are. At least some people are. Okay, so let's see where we're at. So we're Thursday, February 18th. Yes, we're looking at finding concentrations of species in solution given Ka and a bit of introduction to buffers. That's what we'll be doing today. Just a little bit of a look ahead. We'll finish the material pretty much next week, and then on Tuesday of the week before spring break, there'll be a review, and then the test will be due on the Thursday before spring break. There won't be class that day. So as I keep on saying, there's a fair amount of material in this test, and waiting until the last minute to look at it is going to be pretty harmful to many of you. So I recommend getting into it now and starting to study the test questions as we go through them. I feel like a broken record in that respect, but you know. Okay. So let's look at finding the concentration of species in solution. Let's get rid of this here. Up to this point, we've looked at how to calculate the Ka value, but we can actually manipulate this differently as well. If we're given the Ka value, we can actually find the concentration of species that are in solution, especially those of weak acids. Now, a weak acid, as we talked about earlier, is one in which so we'll have a let me do this again here. I'm going to stop sharing for a second. I'm going to go close down something in another profile. Something is slowing my computer down here. I've got to figure out what it is. Okay. Thank you, folks. Sorry about that. I think this will speed things along a bit now. So what we're looking at when we're talking about weak acids is that we're not getting very much of the ions here. So what we're seeing is we're getting this here, but this might be like still very slow here. I'm gonna have to cancel this here, close this down, and reopen it. See if that will help. Okay. All right, give me a second here, folks. I'm sorry. Something is really amiss here. I'm not sure exactly what's causing this. All right. It's freaking Adobe, I'm sure it was, that was causing the problem. I'm not very happy with that program. Okay. Yes. Now suddenly things speed up once I close that down. Okay. Well, maybe not. I'm sorry, folks. This is still not working properly. Okay. Let's try that again. All right. That's looking like it's going to be better now. Okay. That's better. Okay. All right. Now we're getting somewhere. So we have like 98% of the acid and only 2%, or actually we'll say even less than that, less than 5% of the A minus and the H plus, and that's what we're getting at here. Now, when we're expressing this, we can express it in two ways. We can express it as H2O plus HCNO gives H3O plus CNO minus, or we can just express it a little bit more simply as HCNO gives H plus CNO minus. So both of those are equivalent when we talk about these processes. But if you look at what the example is asking, it's asking for the concentration of H3O plus. So it kind of makes sense that we'd have the water in there and show the water so we can get the H3O plus at the end rather than just the H plus, even though they are the same thing. So when we're doing the table here with the setups, we've got 0.184 molar on the initial concentration of the acid. That's what we're given. You can see that's given in the problem. And then at equilibrium, it'll be what we had observed earlier, 0.814 minus Z, and then Z and Z. So again, the rationale there is that at the beginning of the reaction, we have AH, just AH in solution. And then after a time, so that's initially, then after a time, what happens is that we might get one of these to break apart. And you can see that for every one AH that breaks apart, we get an A minus and an H plus. And I think that's fairly simple there to Z here. So if Z HAs break apart or AHs break apart, then we get one ZA minuses and ZH pluses. Does anybody have any questions so far?
I have a quick question.
Mm.
So I remember when we did this in test one, sometimes it would be like 2Z, sometimes it would be 3Z, depending on the equation that was given.
Mm-hmm.
Is that ever going to happen here?
No, because when we talk about these, we're talking about just the release of one H plus and forming the anion. So it makes it a bit simpler, Alexandra, actually, because
Okay, I just wanted to make sure.
you won't have to deal with any of those. Because you see, for every Z HCNOs that break apart, we get one H trio plus and one CNO minus, or Z CNO minus and Z H trio plus.
Okay.
Okay, so there's no need to worry about those coefficients. All right, so we can go ahead now, and what we're trying to do here is solve for Z, and we do have the Ka value. Now the Ka is going to be H3O plus CNO minus over HCNO. Yeah, the H2O, of course, we ignore. I mean, as we talked about earlier, the concentration of water doesn't really change very much. So there's our Ka. We've given the Ka value as 3.46 times 10 to the negative 4. And that equals, and we can put in the equilibrium concentrations here. Now remember, we're trying to solve for Z here. The thing is, though, if you were to solve for Z in this specific kind of equation, you'd have something that looked like this. Actually, we'll do that. It would be an equation that could be expressed in this way, which is, of course, a quadratic equation. And the way that you could solve for Z then would be negative, was it? Now I'm trying to remember the quadratic equation, b squared. Can somebody refresh my memory about the quadratic equation? No, nobody knows the quadratic equation.
Dr. Musgrave it's I think it's a squared times a squared plus b squared equals c squared.
No, that's it. That's
No?
isn't it negative b plus or minus square root of b squared minus 4ac over 2a, something like that?
That looks familiar.
I'm sorry, you're actually right. Yes.
Something like
Yes.
that. I just couldn't remember the exact form of it. Obviously, if I can't remember the exact form of it, sorry, go on.
I think everything is over 2a, not just the square root.
Oh yeah, right. Yeah, I think you're right. Yeah, it's all over 2a. Thank you. Yeah. Anyway, the point being, we're actually not going to use the quadratic equation because it's a real pain in the rear. And we're going to look for a way that we can avoid using that quadratic equation. So what we do is this. Because it's a weak acid, because it's a weak acid, we can actually make an assumption. And then the next thing you're going to do is ask me, how do you know it's a weak acid? Well, we'll say that, we'll talk about that in a second. Okay, so we can say, well, let's assume it's a weak acid. And what that effectively means is that 0.184 minus Z is effectively 0.184. In other words, Z is so small relative to 0.184 that we may as well just be talking about 0.184. So let me sort of tell you a story here that relates to this. See, as I've gotten older, I've become, my eyesight is not as good as it used to be. And what's happened is that you could have a whole pizza in front of me, but then if you took out less than 5% of that pizza, I still think it's a whole pizza. All right, so that's what we're looking at here. I still think it's an entire pizza. You could actually take 5% of my pizza and I wouldn't have any clue if you took 5% of my pizza. That's what's going on here with this weak acid. As long as 5% of it, less than 5% of it, is dissociating, then we may as well just say that it is just 0.184, which makes our equation then a whole lot easier to solve, because then it becomes 3.46 times 10 to the negative 4 equals Z squared over 0.184. Now you might be saying, well, how do you know that you can do this? Well, here's what I know. If the Ka value is 3.46 times 10 to the negative 4, you can see the Ka is proportionate to the H3O plus, right? You can see that Ka is equal to H3O plus times CNO minus. So if the H3O plus is small to begin with, then that's going to give us a very small Ka value. How small, you might be asking? Well, as long as it's 10 to the negative 4 or less, I think you are safe in trying to make this assumption. If it's 10 to the negative 3 or greater, the chances are this assumption won't work out. Now, we do have to end up validating this assumption, which I'll show you how to do in a second. But at this point, what I'm showing you how to do is solve for the Z value. So in your calculator, the Z is going to equal 3.46 times 10 to the negative 4 times 0.184. And all of that is going to be, that's not very pretty, but that's a square root. So you put that in your calculator, that'll give you the Z value. Does anybody have any questions about putting that in their calculator and solving for Z if you've got Z squared over something here? Is anybody confused about that? So everybody's fine with that? Okay, I'm going to leave this. Sorry, go
Just
on.
for clarification, that's 3.46 times 10 to the negative 4 times 0.184 to the
That's
square
right.
root.
Yeah,
Okay.
yeah. So you're just bringing the 0.184 up to the other side and then finding the
Yep.
square root of that.
Okay.
All right. Now the thing, so that gives us our Z value, which I'll put into another thing here. Wait for that to disappear. There we go. Now what I've got to do is I come up with my Z value, which I think is, see, I think it's 0.00776 or something like that. No, 0.0798. Okay. So once you solve for it, you should have Z equals 0.00798 molar, and we need to then validate that assumption. So we need to validate what we said earlier. So we need to validate our assumption. The way we do that is we take the Z value and divide it by 0.184. And that's the, remember what a percentage is. It's always, percent is always part divided by whole. Multiplied by 100%, right? The part here is the Z. That's what it's split into. And this is the whole. And that means that it's 0.00798 divided by 0.184 times 100%, which comes out to be, let's have a look. What's it come out to be? 4.33%. So if you go back and you look at the initial equation here, it's 0.184 minus Z, Z, and Z. So the Z value is only is less than 5% of what the initial value was of the concentration, which means effectively our assumption was correct. So the assumption is validated, it's less than 5%. So less than 5%. So assumption is valid. What do you think you'd have to do if the assumption wasn't valid, if it was more than 5%? Anybody know? What would you do then?
Would you multiply it by the percent or something like that?
I'm sorry, what was that?
Would you multiply the value by the percentage or something
No,
similar to
no,
that?
you wouldn't do that. What would you do? You'd use the quadratic equation. Yeah, that's what you do. You use the quadratic equation. What we were talking about earlier. So we'd go back to the initial equation up here and then solve for Z using the quadratic equation. Any questions?
Can you show us how to get like the setup for how to put in the quadratic equation?
No, because what do you think the chances of getting something where you'll actually have to solve the quadratic equation are, Alexandra?
Then to
Mm-hmm.
none.
What's that?
Okay.
What's that, Alexandra?
Is it none?
Yes, I'd say less than
Okay.
5%, but really, no, it's none. You're not going to get any situations like that. You,
Okay,
the
cool.
assumption will always be the assumption will always work out to be valid.
Cool.
But you'll still have to obviously be able to do that calculation to figure out whether the assumption is valid or not. Okay, it's still part of the problem solving. All right, any questions? All right, so that gives us Z, and if we go back to our initial question, then at equilibrium, the concentration of HCNO is going to be 0.184 minus Z. Now this requires a little bit of significant figure information here. So if you were to do this for the significant figures, you'll see that it comes out to be 0.176. That's three places past the decimal. and then that's 5 places past the decimal. So the answer comes out to be 3 places past the decimal. And then the rest of it would be the H plus and the CNO minus, which are simply equal to Z, which is going to be 0.00798 molar. All right, does anybody have any questions? And when I say H plus, I mean really H3O plus. Any questions? Okay. Let me shut down some of this stuff here. So the other thing, there's one other thing we have to talk about here, and that is whether the H plus resulting from the dissociation of water needs to be considered or not. Okay, so let me explain what's going on here. If you've got a weak acid, or any acid really, I told you that it's splitting at least a little bit into A minus and H plus. But there's also another source of H plus that's possible, and that is the dissociation of water is also producing H plus as well. So the total H plus in solution, so the total concentration of H plus is really the H plus from the acid plus the H plus from the water. Now the thing is though, that what we know is that the H plus from the water is actually a constant value when it's very small. And the maximum value it could possibly be in any solution is 4.5 times 10 to the negative 7 molar. So it's really 1 times 10 to the negative 7 molar, but we also put a little bit of a fudge factor in there, sort of an error, say, well, it could be 5% either side of that. So we make it 4.5 times 10 to the negative 7 molar as being the maximum concentration of H plus from water. So that's the max H plus from H2O. So that's what we're looking at here at the 4.5 times 10 to the negative 7. So what we need to do here is we look at the H plus from the acid and we try and figure out whether that would matter or not. And it turns out if the H plus from the acid is greater than 10 to the negative 5 molar, say about 10 to the negative 5 molar, the H plus from the water won't matter. Does anybody have any questions so far? So let's explain why that is. So if you, let's say we'll look at the example we just did. So for example, if we make the H plus from the acid 0.000798 molar, I'll open up another thing here. Then what you can do is we're looking for the total H plus again. Would be 0.000798 plus 0.00000045. That's 4.5 times 10 to the negative 7 expressed as a decimal. And if you were to put that in your calculator, it would still come out to be 0.000798. So what I'm saying is that this value is so small relative to the H plus from the acid. Remember, that's the H plus from the acid. And this is the H plus from the water. That it doesn't change. So obviously there you can see that the concentration of H plus from water would not need to be considered in that instance. If the H plus from water, as long as it's greater than 10 to the negative 5 molar, you don't need to worry about it. I mean, you don't need to worry about the H plus from the water. Now, if it's less than 10 to the negative 5, you can see that by adding these two things together, excuse me, you might get, you might actually get this affecting the significant figures. But in this instance, with there being so many decimal places, it just doesn't matter. Does anybody have any questions?
I know you'll probably show this in a second, but on a test question that has to do with this, is it going to be like we have to find H plus first and then answer that question?
No,
Or will
I
you
think
give us H
no,
plus?
I think what I do in the question is I give you H plus,
Okay.
and then you've got to determine whether or not the H plus from the water will matter or not. But the bottom line is, if the H plus I give you is greater than 10 to the negative 5 molar, then it doesn't need to be considered because it's too small to be worried about, the H plus from the water.
Mm-hmm.
But if it's less than 10 to the negative 5, then you would need to consider the H plus from the water because it would affect the calculation. Is that okay?
Yeah, all that makes sense.
Okay, good. But yeah, I'll show you that question in a second as well. All right, any other questions? So you can see here that in the answer to this question would be, because the answer, the H3O plus is 0.00798 molar, that's for the HCNO, that's what we just calculated. This far exceeds the H plus for the water, adjusted for the 5% rule, which is 4.5 times 10 to the negative 7 molar. Therefore, the H plus from the dissociation from water is negligible and need not be considered here. So we're saying that the H plus from water is so small that it doesn't matter. All right, any questions? Okay. Let's take a look. Let's take a look at the test questions here, and you'll see what we're talking about. Let's take a look. No, I didn't mean to do that. Sorry about that. I meant to hit preview. There we go. Okay, so these are the these are the kinds of calculations we're talking about. Calculation of pH and HA from Ka. So that's what we're doing. So here what it's asking for is the pH of a 2.89 molar solution of HA, but has a Ka of 7.87 times 10 to the negative 5. Okay, so here's what you would do. HA is going to split into H plus A minus. The initial is going to be 2.89 molar, 0 and 0 on the H plus and the A minus. At equilibrium, we've got 2.89 minus Z, Z and Z. So the Ka then is going to be equal to H plus times A minus over HA, which would be Z squared over 2.89 minus Z. And what we're going to do here is we're going to assume that 2.89 minus Z is going to be 2.89. So we're assuming that Z is so small relative to 2.89 that we don't have to worry about it. Now the Ka value is 7.87 times 10 to the negative 5. So we're justified in doing that because if this is such a small Ka value, that this will probably work out, it probably will be valid. So you can see it becomes 7.87 times 10 to the negative 5 equals Z squared over 2.89. And then we can solve for Z. Can somebody do that for me, please? So you'll do 7.87 times 10 to the negative 5 times 2.89 and take the square root.
I got 0.015081.
0.0150 or 151?
Yeah.
Okay. So Z is 0. That sounds about right. So that's what Z is. Now we can, you really don't have to validate this because it's not asking you for that. It's really just asking you for the pH. But let's say let's do the validation part just for kicks anyway. So validate. And what we'll do is Z over 2.89 times 100%. And Z over, not Z, 0.0151 divided by 2.89 times 100%. Can anybody give me a figure for that?
I got 0.522.
A percent? Yeah, okay.
Yeah, after I times it by 100.
Yeah, okay, good. Yeah, 0.522 is good, I think. Oops. Yeah, 0.522%. That's clearly less than 5%. So it looks like our initial assumption was valid. So the Z value, as we came out with, is 0.0151 molar, which happens to equal, if you look here, the concentration of H plus. To get the pH, it's going to be the negative log of the H plus concentration. So it's negative log of 0.0151. Can somebody come up with an answer for that, please?
I got positive 1.821.
Okay, so yeah, it'd be 1.821. That'd be three significant figures, which means 3 places past the decimal. So make sure that you can get that. There's no unit on a log here. So the pH should be 1.821. Does anybody have any questions? Now, when you answer these questions, as long as you get it within a certain tolerance, it'll give you the right answer. Okay, so there's a tolerance, and the tolerance doesn't really take significant figures into account either. But if you do it correctly by significant figures, you should get the right answer. All right, any questions? It's not a difficult calculation, not really. Okay, question 13. Calculate the percentage that allows for the deliberation of whether or not 0.04 minus H plus is approximately 0.04 in accordance with the 5% rule. So 0.04 molar solution of HA with a Ka of 5.01 times 10 to the negative 6. So what you're being asked to do there is pretty much what we just did. And you will have to be able to calculate this here, the concentration of H plus in solution. So we're starting out at 0.04. And then 0 and 0 at equilibrium. It'll be 0.04 minus Z, Z and Z again. We know that the Ka is equal to H plus times A minus over HA. And the Ka value is 5.01 times 10 to the negative 6. And that's going to equal Z squared over 0.04 minus Z. So we're going to make the assumption, assume weak acid. That means 0.04 minus Z is approximately equal to 0.04. And then we can solve for Z, now that we have that information, Z squared over 0.04. Can somebody do that for me, please? Calculate Z. So it'd be 5.01 times 10 to the negative 6 times 0.04, and then take the square root.
I got 0.000448.
0.0, how many zeros? 0.
3 zeros after the decimal point.
Okay, and then 448?
Yes.
Okay. So this is really just after a determination of the percentage here. Effectively, I guess it would be one significant figure. So what you would do is you would do Z to see it to validate the assumption. It would be Z over 0.04. and times 100%. So it would be 0.00004 divided by 0.04, which I think is going to come out to be 1%. Is that right?
Yeah.
Yeah. And that would be your answer, be 1%. So, and that would be less than 5%. So that would be valid. But that's not what you're after here. You're just looking for so it just says the answer to 2 decimal places, even though this might violate significant figure rules. So, so maybe I think in this case, you're probably better off taking it out to that many figures. So make it 448 divided by 0.04. If you did that, what would it be? If you did 0.00448 divided by 0.04.
1.12.
1.12. So I think that would be the answer I'd put in there. So I'm asking you to pretty much ignore significant figures here. So with this question, just because of just because I don't want you keeping it to one significant figure to make this calculation work. But the point is that it comes out to be less than 5%, which would make it valid. Does anybody have any questions? Okay, number 14. It was determined that H plus was initially 0.00725 it was determined that H plus was 0.00725 in an initially 0.310 molar solution of HA. What is the new concentration of HA with the correct number of significant figures? So for this one, you've already been told what let's have a look. This is what you're told in the problem. So HA gives H plus A minus. You've got your initial, which is 0.310. 0 and 0. And then you've got 0.310 minus Z, Z, and Z. So so we know that what we're looking for is the new concentration of HA, and you're told what Z is. Z is actually 0.00725. So we know that the concentration of HA is going to be 0.310 minus 0.00725, which would be in this case 0.303. And that would be your answer there, 0.303 molar. So that's the part of the question it's looking at. Does anybody have any questions? Everybody's okay with that, huh? All right. Okay, so looking at number 15, I think this is the last one. Yeah, that's the last one, this question set. Given that the concentration of H plus is 0.00409, see, and I give you the value there, and that the H plus for H2O is 4.5 times 10 to the negative 7, does the H plus from water need to be considered? So you just need to look at the value I give you here in question and evaluate whether it's far greater than the 4.5 times 10 to the negative 7. So the question is, if you add them together, does this value really change? In this case, it wouldn't. So you'd have to find the answer that matched that. But I'm not going to say what the answer is. You can work that out when you go through the test. Does anybody have any questions about number 15? All right. Any questions about any of those questions that relate to to this question on the test. All right. Okay, so let's go through. We'll do a little bit of stuff on buffers. Now we've already talked about buffers a bit here. We talked about them when we were doing titration curves a bit earlier. Now, I don't really want to go back into the whole thing with the titration curves. If you haven't seen that lecture yet, then I'd recommend you go back and view it. A buffer is a solution of a weak acid and its conjugate base prepared in such a way that the solution will resist large changes in pH upon addition of small amounts of strong acid or base. So this is something we've been looking at and dealing with in the lab as well. So you're getting to see this in practice too. So we have the weak acid here, which has the equation AH gives A minus and H plus, with the realization that this is going to be small. So this isn't going to dissociate very much because it's a weak acid. And it has to be a weak acid for this to work. So I'll go through the blurb here. So you've got a buffer, which is going to be a combination of AH, and A minus is going to also be in there as well. So this is what's meant by a solution of a weak acid, which is AH, and A minus is the conjugate base. We talked about this, I think, in the last class as well. The H plus was removed from the weak acid. That's how we got the conjugate base. So let's say we're adding a strong acid in. So what's going to happen is that the H plus will react with the A minus and it will form AH. See, the H plus can't react with the AH, but it can react with the A minus. Now, if it does that, then after that's happened, we'll have 3 AHs and we'll have an A minus there. So we'll add in another H plus, we'll do the same thing. And that means we'll have 4 AHs then. But you'll notice that what's happening here is the pH is only going up very slightly, because all we're really doing is increasing the amount of AH. And then what will happen is that we add the H plus in here, and that will overrun the buffer at that point, and we'll have H plus in the solution and AH and AH. And at this point, we have a drastic rise in pH. So pH rises very slowly, or sorry, pH falls slowly here. So that's what's meant by resists changes, large changes in pH upon addition of strong acid or base. So you're adding the H plus here, and you can see what's happening is that the pH will fall slowly here, and then it will fall drastically here once all the A minus is gone. Does anybody have any questions? Everybody's okay with that, huh? Okay, let's look at let's look at what happens when we add base then. Same kind of thing. So we'll start out again with the 4AH, the AH, the AH, the A minus, and the A minus in the solution. So that's the buffer. And we're going to add in the strong base, which is the OH minus. Now the OH minus won't react with the A minus, it will react with the AH. And it will form A minus plus H2O. So as we add in the OH minus, what happens is that the AH turns into A minus. The pH is going up slightly at this point. We'll do the same thing again. And we'll just have A minus, A minus, and A minus. So up to this point, the pH has been slowly rising, or slowly going up. And then after we add the OH minus in and there's no more AH to react with, we end up having OH minus and then A minus, A minus, A minus, and A minus here. And that's going to give you the a drastic rise in pH. Does anybody have any questions? Anybody have any questions? All right. So the kind of questions you're going to have to be able to answer about this are going to revolve around the calculation. And I'm going to show you, first of all, how we get the pH of a buffer solution. And I'll go through that calculation here. So a buffer is made up of equal volumes, 100.0 mils of each of 0.100 molar acetic acid and 0.105 molar CH3COO minus. So you can see how we get the acid, which is AH. And then if we want to get the conjugate base, so that's the acid or the weak acid, let's make sure we say that weak acid. The conjugate base then is going to be A minus, which is CH3COO minus. You see all we've done is taken the H plus off here. That's the conjugate base. Now, if you look at the mixture here, it's a mixture of 0.100 molar acetic acid and 0.105 molar CH3COO minus. Notice they're not the same concentration, but they don't have to be. First of all, we need to find the pH of this buffer solution. So how do we do that? Well, we've got our equation here, which I'm going to adjust a little bit. I'm going to take out the water, and we'll just make it CH3COO minus plus H plus. So initially, the concentration is going to be 0.100. So initial concentrations. Let me make that a little bit clearer. So the initial concentrations will be 0.100 of the acid and 0.105 of the base, and there won't be any H plus in solution at this point. At equilibrium, what's going to happen is that we're going to lose a little bit of the acid, and we're going to gain a bit of the conjugate base, and we're going to get H plus as well created. So this is at the very beginning. When we mix them together, there is no H plus, but the H plus does come from the acid here. Now what we can do is the same thing as we did earlier, and we know what the Ka is because we're told that it's 1.80 times 10 to the negative 5. So we know that Ka is going to be CH3COO minus H plus over the CH3COOH. So we know what the Ka is. It's 1.8 times, or 1.80 times 10 to the negative 5. And then we can substitute our values in here. We've got 0.100 minus Z. No, start again. 0.105 minus Z times Z over 0.100. No, it's plus Z up top there. 0.100 minus Z down the bottom. So we're just substituting in these values here at the equilibrium. Because it's a weak acid, we don't even have to assume it. We're told it's a weak acid because it's a buffer. So buffer is equal to weak acid, because that's what a buffer is. So the buffer is a weak acid. So what that means is we can assume, without even validating it, that 0.100 minus Z is going to be 0.100, and 0.105 plus Z is approximately 0.105. So then we can solve for Z a lot more easily. So it'll be 1.80 times 10 to the negative 5 equals 0.105 times Z over 0.100. And then we can solve for Z, and it comes out to be, in this case, 1.71 times 10 to the negative 5. Now Z happens to equal the concentration of H plus in the solution. So the pH is going to be the negative log of 1.71 times 10 to the negative 5, which comes out to be, in this instance, 4.767. And remember, with the significant figures here, it's going to be 3 decimal places on the log, because 3 significant figures here on the pH, or on the concentration of H plus. So that's how we'd find the initial buffer concentration. Does anybody have any questions? So the next part of that question then, which I'm not going to go through completely today because it's a fairly long calculation, we don't really have time to do the whole thing today, is we would then look what happens when we add a small amount of either strong acid or strong base to the solution, and figure out what the new pH is. So this gives us a pH, and then if we add, in this case, strong base, we expect that pH to go up. if we added strong acid, we expect the pH to go down, but not by very much. It's only going to be a small amount, but we're actually going to do that calculation. So we're going to leave that for Tuesday, showing what happens when we add the small amount of strong acid or strong base to a solution, pH. All right, does anybody have any questions? Anybody have any questions? Okay, all right, well then we'll leave it there for today, and I will see you all on Tuesday. Thanks for coming.